for reasons best known to Google Meet. I don't know. Okay, let's continue. So yeah, um, we have learned a lot about the Gaussian elimination. This week we want to talk about norm, matrix, and norm, vector norms, and also condition numbers. I'm going to be meeting everyone. If you want to say anything, please raise your hand. I'll give you the opportunity to unmute yourself. Just tap this button to raise hand when you want to speak, all right? So that we won't be having interference. Okay, here are my objectives. I believe you guys have your notebook by your side. It's important to take notes, all right? So, like I said, the topic for today's lecture is matrix and vector norms, condition numbers. I have these learning objectives. By the end of this lecture, we should be able to define and compute vector norms, all four norms. We will talk about the L1 norm, the L2, L infinity, and LP norms. Then we should also understand the norm axioms and the properties. You should be able to state the norm axioms. If I tell you this is L1 norm, you should tell me the axioms of the L1 norm or the properties of the LP norm. And then compute the matrix norms that is induced by different norms. We also have the Frobenius norms. You should also be able to calculate the condition number of a matrix, which is a very important quantity that determines the solution of any system of linear equations. And the ability to interpret condition numbers for numerical stability is also something we're looking at achieving by the end of this lecture. And relates residuals, error, and condition number. What is their relationship? How did they relate? How do they work together to getting you some interpretation to a solution of any system of equations? I should also be able to analyze sensitivity of linear systems, identify well-conditioned versus ill-conditioned systems. So when you see a system that is well-conditioned, you should be able to identify it by the end of this lecture, as well as ill-conditioned systems. Then apply these concepts, whatever concept, all the concepts we'll be learning, to past examination problems. We will solve some past questions. I think when I come back to Abuja, the first class we'll be having the first physical class we'll have when I return to Abuja would be questions that will solve problems, right? Problems from all of the topics we have learned so far, so good. Yeah, then we'll then apply the norm and condition number computationally. We're going to write some code, Python codes to solving some of these systems. All right, so these are the list of the topics we'll be covering: vector norms and their properties, matrix norms, that is operator norms. We're going to look at the Frobenius and the spectral norms, condition number, this kappa A. So this is what we call the condition number. Condition number is presented as kappa of A equal to the norm of A times the norm inverse of A, all right, or the inverse norm of A. The norm of A times the inverse norm of A. That's how to obtain a quantity which is referred to as the condition number. It's presented as the kappa of A. This is K, right? This curly A is not like the English letter A, but it is the Greek letter kappa of A. Then we'll also cover error bounds and sensitivity analysis, computational techniques, applications to real problems. So I believe we are fired on to, we are motivated enough. But let me say motivate you some more before we go further into the topic. Now, don't write this. This is just a way of me motivating you and letting you see reasons why we should look at the norm. So it's starting from the perspective of measuring size and sensitivity. The first question you might want to ask yourself is, when can we trust a computed solution? Remember, we've solved systems of equations already for previous lectures. You've seen various methods of how to compute a system of solution. So when you look at a system that was modeled from maybe a physical solution in terms of medical field, some medical, let's say we're looking at medical field and trying to model some medical procedures using mathematical models so that we can solve such system, and that will be excuse me, that will be tied to life. So when do you say as a mathematician that you can trust a computer solution that is even related to life? I'm just using this as an example. That's what we want to look at now. I would like you to start by considering the solution for this system AX equals B numerically. Now, how do we solve this? We start by computing the estimated solutions, that is X tilde, instead of using the exact solution, X, all right? Oh my God. I don't have water around. And then some critical questions you might want to answer. Number one, how do I, yeah, thank you. The first question, how do we measure how far from, thank you very much, how far from how well? Someone's hand up. Is anyone seeing the screen? James, aren't you seeing my screen? If you can see my screen, please can you give me a reaction? James is not seeing my screen. Okay, Christopher, I believe that. Okay, so James, I guess your network is not stable. That's why you see my screen. So the first question is, how do we measure how far we are from the actual or the exact solution? If we have small residual, that is the norm of the difference between the B, don't forget what B contains. B is a column matrix or the column vector of the constants in the system of equations. When you take the difference of that B and the product of matrix A by the estimated solution, that is A times X tilde, taking the norm of those, of course, you know, the norm is just the distance in a higher dimensional vector space. Now, if that is X tilde is close to X, if we have small, that is X tilde is close to X, that is another critical question you want to answer. Now, the third part is, if the data A or B, what is A? Don't forget, A is the coefficient matrix, that is matrix that contains the coefficient of the system, while B is the column vector that contains the constants. Now, if the data has small error, remember that in the real world, most times these data are gotten by measurements and observations. When you carry out experiments, the experimentation can be a process of just observing things around. You're taking measurements. And if by observation or experiments you somehow, by mistake, introduce small error to your data, will the solution have small errors? That's a very vital question. When you introduce small error to your data, will the solution also have small errors? Then, can we predict beforehand if a solution will be sensitive to errors? These are critical questions that lead to the topic we're going to be resolving or talking about today. Critical question. And what's the answer to all of these questions? The condition number, kappa of A. It tells us everything we want to know. Once you know the condition number, you can tell how to measure how far we are. You can tell if we have small residual in the difference between the constant vector and the product of the coefficient of matrix with that estimated, see how close it is to X. You can tell if small error in the data will result to small error in the solution. We can also predict beforehand if the system will have sensitive errors. Now, that is the condition number. Now, how do we estimate this condition number? Because it is very important. How do we estimate it? Again, still on the motivation example, look at this. We are not writing here too. I'm just going over the motivation. Look at example 3.1, motivating example. Let's consider this system. Here is a system. We're still working with 2 by 2. Well, I'm trying to use the simplest example that can help you understand or see things from at least a lower dimensional space before we go into something more technical. All right. So when you consider this particular example, we have the matrix of coefficients, which is the identity matrix, right? 1, 0, 0, 1. Then we have the variables x1, x2. And then we have the constant 1, 1. The solution to this system displayed on my screen, that is the solution to this very system, is nothing but the solution to this system matrix, equation 130 is nothing but 1, 1, 1, 1. The solution is 1, 1. That is when you take the transpose of this row matrix 1, 1. That's the solution to the system. By introducing a slight change in the constant matrix, that is, when you make this 1 here become 1.01, and the other one remains as 1, like this. By introducing a slight change in the coefficient or the constant matrix, the solution becomes this. Remember, the solution has 1, 1 as a component. When you change the first component on the vector, column vector for the constant values, you have a similar solution, which means that small change in the data returns to small change in the solution. Of course, small. That's for system 1, system 130. Now, by the time we introduce a smaller change in the system, right? We make this become 1, 1, 1, 1, 0, 0, 0, 0, 1. No longer the identity matrix 1, 0, 0, 1. Okay, with a constant 2, 2. Now, if we have a slight change in this particular constant matrix, instead of having 2, 2, we have 2.01 and 2. What then happens to the solution? The solution becomes approximately -98 and 100. Where did we come from? We are coming from here, a solution of 2.0. By just introducing a tiny change in the data, that resulted to a huge change in the solution. Do you see that? Because we are dealing with a different system. Now, the question is why? Why did we notice this? Now, we noticed this because system 2 has a large condition number. It is approximately equal to 40,000. That is the condition number for system 2. Of course, you can estimate the condition number for system 1. What's the formula again? I need you guys to note that this formula is a very important formula. This is a formula we use in estimating the condition number for any system. All you need is know the matrix of coefficients, estimate the norm of that matrix, then take the product of that norm and the inverse of the matrix. Once you calculate that value, that quantity is what we call the condition number. And the condition number tells you, it gives you some insight into what the solution will be, even before calculating the system or solving the system actually. So what are some real-world importance of what we just discussed? Number 1, in engineering, it is used by structural analysis with measurement errors. In data science, we use it a lot for regression with noisy data. If you have noisy data, it's being used to handle sort. For image processing, for reconstruction from corrupted images. In economics, it is used in the input-output models with uncertain data, and in climate modeling, predicting with parameter uncertainty. So these are some of the real-world applications of this what we just said. So with this little motivation that we have given, let's dive deeper into this lecture by looking at the first concept that we'll be considering today, the vector norm. So I think at this point, if that's all right, the vector norm, this is the first concept we'll be introducing to us, because we said the condition number. Olamide, please put off your mic, except you have a question. If you have a question, raise your hand. I will allow you to unmute yourself. Is that okay? Olamide, can you hear me? Okay, I'll do that for you. So, because to calculate the condition number, you must know how to estimate the norm of a matrix. Now, let's start by introducing what's the norm. Let's start with vector norms. What's the vector norm? I know you're learning that in your functional analysis now, Maths 412. Is functional analysis Maths 412? What's the math code for functional analysis? What is the code, the course code I need to say? Bala, What is the course code for function analysis? Now this is the time for you to unmute your mic and talk. Now you need to unmute your mic. Bala, can you hear me? I hope I've not been speaking to myself. Yeah. Hello? No. Hello? This is my students. You are wonderful students. So how will I be speaking and nobody is responding or saying something? Can anyone hear me at all? Okay, let me say something now. It's not prohibited to speak in my class. What is prohibited is talking without taking permission. All right, you want to speak? Yes, you can speak, but you raise your hand, I'll give you opportunity to speak. Now, if I ask a question and you have an answer to the question, just go ahead and answer. So I just asked a question now, nobody's saying anything. Joseph, can you hear me? Joseph. Wow. People have come against the network code. James, can you hear me? Okay, if you can hear me, give me a reaction. Bala can hear me. Excuse me, guys. Why is
So our hearing is just the network. It's somehow cracking. And sometimes one needs to go off.
okay? No problem. I will continue. I'll continue. But if you guys, okay, well, that's fine. I'll just continue anyways. So the vector, please write vector norms, definition 3.2.1, definition and axioms. A norm on Rn, is a function, which is defined as the norm of dots from Rn to R. So this is just the generic way of defining a norm in Rn. Is a function that maps vectors from Rn into the real number line, into R. So whenever, this tells you that whenever you compute the norm of any vector in a vector space, the result is always a real number. And what are the properties? What should you look out for you to say, oh, this is indeed a norm? Number one, the norm must satisfy the following properties. Number one, positivity. Positivity. It means that the norm of any vector in the space must be greater than or equal to 0 for all x. And it's going to be equal to 0 if and only if the vector you're considering is a 0 vector. That's what we mean by positivity. So you see any function in Rn that maps elements of Rn to R. Before you conclude that that function is a norm or is a vector norm, the first thing you have to look out for is what? Is the positivity property satisfied? And how do you define the positivity property? When you take the norm of the vectors in that space, are they always going to be greater than or equal to 0? Then the second question you want to answer, is that function homogeneity? That is the homogeneity part of the property to be tested. What do you mean by homogeneity? It means that when you take the norm of a scalar alpha and a vector, that is a dot product of the scalar and vector, the norm of that dot product, it has to be equal to the product of the absolute value of that scalar and the norm of the vector for all alpha in R and X in Rn. This is homogeneity. And once that function satisfies the two properties, positivity and homogeneity, the third property you want to look at for is called triangular inequality. Triangle inequality. Triangle inequality. Does the norm or the function, does it satisfy the triangle inequality property? What does it mean mathematically? It means that when you take two vectors in the space, x and y, you sum the vectors, you add them up and take the norm of those vectors. The answer you get, is it always less than or equal to the summation or the addition of the norms of the two vectors for all x and y in X and Rn? If that's true for all the vectors, if these three properties are satisfied, then you can jump into conclusion and say that the function defined above that picks elements from Rn into R is a vector norm. Do you understand? Do you understand what I just said? If you do, give me a reaction, please. I hope I wake you up from sleep tomorrow and ask you to define a vector norm. You know what to do, or you know what definition is. Give me a reaction if you guys understand, please. I'm not getting a reaction, guys. Am I audible at all? Okay, Sulaiman, thank you for the reaction. Okay, what's the remark? I have a remark for us. Remark 3.1. A norm generalizes the concept of length. If you're interested or if you are familiar with the concept of length or magnitude in metric space, you did metric space in what course is that or what level? I think it should be your 300 level. 300 level in metric space in vectors, right? Metric space is taught in what course again is that? Okay, no, in topology. No, metric, not norms. I think you have learned metric from your linear algebra or vectors. So this same concept of norm is something that's taken from your topology or your algebra, linear algebra concept into this numerical analysis from Euclidean geometry to abstract vector spaces, like I said. So it's something that has to be, in fact, right from secondary school, I just remembered now, right from secondary school, you remember when you talk about vectors on R2, that is, you have your plane, the X, you have the Y axis, you also have the X axis. You have the Y and the X axis. If you have a vector that starts from the origin, let's call it vector A. All right. You're told to calculate the magnitude of vector A. How do you calculate the magnitude? The magnitude is equal to x squared plus y squared. That's magnitude. Now, this concept from R, in fact, even on R, I'm even going to Rn actually. The concept from R, that is real number line, that talks about the distance function 1, 2, -1, -2, and so on and so forth. I ask you, what's the distance function from 1 to 3? What's this particular distance? This distance is the absolute value of A. And the absolute value of A simply tells you the size, the distance of A from a fixed point or from the origin. Yeah. And when you look at that distance function, these properties are also satisfied. Positivity, homogeneity, and triangle inequality. Now we are taking that concept into a higher dimensional space. And when we get to a higher dimensional space, we no longer call it absolute value, but we call it norm. Am I making sense? I need to be seeing reactions on this call, guys, for me to confirm that you can hear me and I am communicating. Please, are we together? Okay, next, let's look at this another definition, the standard vector norms, definition 3.2. We have given a general definition of norm. This is how to identify a norm generally. Let's begin to look at some specific vectors or some specific norms. There are some norms that are called the standard vector norms. I'll start with the first one, P norm. The P norm. Right, please. For x equals x1, comma, x2, comma, dot, 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 comma, xn. C, that is the transpose of this row vector. P is an element of Rn, and P is a number greater than or equal to 1. The P norm is defined by the norm of xp, you write P by the subscripts. This is what we call LP. So LP is defined as the norm of x subscript P equal to the summation of all xi's to the power of P, where I ranges from 1 to n, on to brackets raised to the power 1 over P. Is this norm familiar to anyone? Let me hear you. This norm, is it familiar to anybody? Olamide, does this norm look familiar to you? Does it look like something that you've seen before? Olamide, unmute your mic and talk to me. I am not familiar with it. That is not true. Why aren't you unmuting your mic? Talk to me, Olamide. I want to hear you. Moses, the norm described at line 132, is it a familiar norm? You should talk to me so that we can continue this class. If you're not saying anything, I will not continue. I will stop and just be looking at your. I can't speak for the rest. Olamide, I want you to unmute your mic and talk to me. I need to hear somebody speak with me before I continue. Olamide, talk to me. Let me hear you. Unmute your mic. Or you don't know how to. Okay, go ahead. This norm, is this something that you're familiar with?
No, not learned it, but the formula is not something that is difficult from what I'm saying.
Okay. But do you know how to calculate the in coordinate geometry, do you not calculate the distance between 2 points? Or let me say the length.
Yeah. And
Do you not do
sir,
that? Yep.
sir,
Mm-hmm.
sir,
I can hear you. Go ahead.
Chris network and some of my colleagues are in the mathematics lab right now in school. Their network is not bad. It's very bad. So they are unable to connect.
Oh,
So we are
wow.
watching it together. They are with me.
Oh, okay. Okay. How many of them are with you?
Chris and Bala.
Okay, Chris and Bala. Okay.
Yes.
That's noted. That's noted.
Sir?
All right. I said that's noted. It's okay. It's fine. It's not a problem. So what I'm saying now is that you may not all see this norm as express as, when I say express, I mean as explicit as it should be. But I'd like you to know that this same thing is what I have described here. This is same thing. Let's say I represent this using x1 squared plus x2 squared with a square root, right? This is the same thing as saying x1 squared plus x2 squared, all raised by 1 by 2. True of course, according to the indices, the square root of any term is like writing that term to the power of 1 by 2. Do you agree with me? Do you agree with me, please? That means I can also write this as equal to the summation of xi raised to power 2 as I ranges from 1 to 2, all raised to power 1 over 2. Is that correct? That's it. Now, if you look at it now, what's the difference between this and this? Don't they look very similar? Of course, they look very similar. The difference is that I have not added the absolute value, right? I haven't added the absolute value. And once I add the absolute value here, this becomes the LP norm. So in this case, this is L2 norm. LP. So P can be any number greater than 1. P can be 2, 3, 4, 5, and so on and so forth. So this is what we call the LP norm. Then the three most important cases for the LP norm. Aha, I can see I described them very well. So we have the common vector norm. When P is equal to 1, we call it the Manhattan or the taxi cab norm. Manhattan norm or the taxi cab norm. So in case you hear me say using the Manhattan norm or using the taxi cab norm, you know what I'm referring to. It means that it is the LP norm where P is equal to 1. So when P is equals 1, this is how the LP norm is being explained or expressed. It is just the summation of the absolute value of xi, where I ranges from 1 to n. Then when P is equal to, we have the 2 norm, which is the Euclidean norm. That is the example I've just cited up here. Then we have this as the absolute value of x subscript 2 equal to the square root of the summation of xi raised by 2, where I start from 1 to n. Exact explanation I just gave right here. And then this is also written as just the norm of x by default without adding any subscript. Then we have the infinity norm, which is referred to as the maximum or the Chebyshev's norm. The Chebyshev's norm. So I have given 3 types of norm: the common vector norm, the Euclidean norm, and the maximum or the Chebyshev's norm. How is that computed? That is computed as the maximum of the absolute value of any number in a given vector space where I ranges from 1 to n. So when you have different vector points, what is the maximum? When you have different vectors in a space, if you're asked to use the maximum norm or use the Chebyshev's norm from all the vectors in that vector space, what is the maximum norm, the vector with the maximum norm? That's the answer to the question. Just pick the vector with the maximum, that's all. So the question is, why the infinite norm? I'll take that as a remark 3.2. The infinite norm is actually the limit of that your LP norm. The infinite norm is the limit. How is it seen as a limit? So you can look at it. The infinite norm is the limit of the norm of norm P, where P, is tends to infinity. That is taking the limit as P tends to infinity of this LP generalized norm or common norm. That is, as P tends to infinity, the largest absolute value of xi dominates the sum. As P grows, the largest vector norm or the largest norm in the vector space dominates the sum of all the norms. All right. Let's move forward. Let's look at an example. Examples and computations. Example 3.2. This example says for x equals the column vector 3, minus 4, 0, and 12. This x can also be written as 3 minus 4, 0, 12. So this is x written as a column vector. We want to compute all three norms. We want to calculate all the three norms. One norm, the two norm, the infinite norm. Look at it here. The one norm is just saying, hey, take the summation of all the absolute value of xi, where I ranges from 1 to n. And that's what we have here. So that is sum of 3, the absolute value of 3, plus the absolute value of minus 4, plus the absolute value of 0, plus the absolute value of 12. And that gives 19. Straightforward. That is the L1 norm. Equals 19. The L2 norm is saying take summation of the square roots of the summation of all xi squared, where I ranges from 1 to n. That's the Euclidean norm. And how do we obtain that? That is x3 plus negative 4 squared plus 0 squared plus 12 squared. And of course, 3 squared is 9, negative 4 squared is 16, 0 squared is 0, and then x squared is 144. When you add these values up, that will result to 169, and the square root of 169 is 13. So this is the Euclidean norm. Then the L infinity norm is saying take the magnitude of each component in the vector, then of all the magnitude of each component, pick the maximum, pick the largest, and the magnitude or the absolute value of 3 is 3, the absolute value of minus 4 is 4, the absolute value of 0 is 0, the absolute value of 12 is 12, which is the maximum, 12. And this is the L infinity or the infinity norm. Now, what do we observe? We observe that the infinity norm is less than or equal to L2, that is the Euclidean norm, and the Euclidean norm is less than or equal to L1, which is the one norm. And this is always true. It is always true in any instance, any example. So I hope with this explanation of mine, you can now calculate the norm of any given vector in a vector space. True or false? Are we good? Please confirm you can see hear me. I want to be sure of your network so that I'm not talking to myself. Olamide, can you guys see hear me? Alhaji Bala, thank you for your reaction. It means we are all on the same page. Beautiful. Can we forge ahead? Can we move forward? I'd like to show us a geometric interpretation of the norm in R2. What's the geometric interpretation? This blue square, this blue square, right? No. The green square represent the infinity norm, and the red circle represent the L2 norm. This is what it means geometrically. So I am working with a vector x that starts from the origin to the circumference of the circle. That is the vector x from the origin to the circumference of the circle. Now, the distance or the length of the vector x itself, the actual length, is actually equal to the radius of the circle, the absolute value of the radius. Of course, radius is always positive. Do we see that? That's the actual length of the circle, not circle actually, the actual length of the vector. Now, but there are three norms defined: the norm in the blue, the red circular norm, and the green squared norm. Now, the norm from this pictorial representation that is very close to the actual length of the vector happens to be the Euclidean norm. But when you check through all these norms, you will see that they are all equivalent to or all approximately equal to 1. That is with unit spheres. All vectors with LP norm is equals 1. This is just the geometric interpretation in a two-dimensional space. Let's take this note down, please. 3.2.5. Norm equivalence. Norm equivalence. I want to see how these three norms that we've defined, how are they related? Remember we mentioned this is part of our objectives, right? How do we relate? How are they related and how are they equivalent? Theorem, we'll talk about this norm equivalence by looking into this theorem 3.1. Theorem 3.1. Somebody just joined my class. Or you went off, I came back again. Theorem 3.1. The theorem says that all norms on Rn are equivalent. All norms on Rn are equivalent, specifically for the P norms. For the P norms, we have that the norm, the infinite norm of x, is less than or equal to the Euclidean norm, and that is less than or equal to the square root of n times the infinite norm. Alhaji Bala, please mute yourself.
Sir?
Don't worry, I'll help you mute yourself. Let's continue. So that's the first relationship we have. Then the next set, we have that the Euclidean norm. Sorry, hold on. Yeah, guys, before I settle down, kindly write down this part of the notes. I want to relocate. Just take a note down before I settle down. Thank you.
Sorry, sir, can you repeat yourself again?
We can't hear
We
you.
can't hear you.
I said you should copy down this part of the notes first. I'm trying to settle down. I want to change my location.
Your network is cracking, though. Your network is cracking. I don't know if it is from our own end. I don't know if it is possible. Just type for us.
Um, Guys, so I said that you should copy down what you can see on my screen. Write it down here, exercise book, while I look for while I change my location. I want to change my location to somewhere else. Yeah, let me continue. Hello, I'm back, guys. No, Anna. Mustafa, can you hear me? Have you guys listened this part of the notes? So we're looking at equivalence, right? We said the norm of x, second equivalence we're looking at, the norm of x, that is Euclidean norm, is less than or equal to the L1 norm. and that's less than or equal to the square root of n times the L2 norm. Check these relationships, and please take it of them, very important. Then the third line says the norm of infinite is less or equal to the norm of 1, and that is less or equal to the n times the norm of infinity. So it's just a little sketch proof that I have for this theorem. So you sketch for the norm of infinity being less or equal to the norm of 2. And how do we proof sketch this? We start by picking a vector xk, an arbitrary vector xk, and take the absolute value of this vector. That vector has to be equal to the maximum of all the i's for xi, and that is equal to the norm infinity. When you let this be equal, this is just like an assumption. So we want to assume that these three quantities are all equal, right? With this assumption, we can go further and say that then the norm of 2, of course, we know how to define the Euclidean norm. The Euclidean norm is the square root of the summation of all xi squared, where I ranges from 1 to n. And that has to be greater than or equal to the square root of x subscript k squared, which is equal to the norm of xk, and that's equal to the norm of x, which is the infinity norm. We know already that the infinity norm is defined as this absolute value of xi's, right? Now looking at it from the upper bound, which is x subscript 2, the norm of x subscript 2, starting from the expression, the Euclidean norm, that's less than or equal to the square root of the summation of the infinite norm squared, where I starts from 1 to n, and that equals the square root of n times the Euclidean norm. All right, that's how we come to the end of this proof. So when you look at it, we have shown that these norms are equivalent, right? So if any one of the two norms that you've shown that are equivalent, then you're good to go. From this, we show that norm of 2 is equal to norm of infinity, which is this side. Then we also showed that norm of 2 is equal to norm of the square root of infinity, which is also which is this side and this side. You know, so that shows the equivalence of these norms. Whenever you're dealing with any of the norm, you know how to relate them. When you're having the norm infinity first, it has to be less than or equal to the norm Euclidean norm, and the Euclidean norm is less or equal to the square root of n times the infinite norm. Okay. So let's verify using inequalities. Let's verify using inequalities. The same vector we worked with the other time, x equals 3 minus 4, 0, and 12. When you pick this vector, when we obtain the norm of infinity, we've gotten the three norms earlier. Let's write it down. We have the norm of 1, the norm of 2, and the norm of infinity. I think we've obtained these three norms. Let's go get the values again. We got the norm of 1 as 19, norm of 2 as 13, norm of infinity as 12. 19, 13, 12. Let's write them down here. 19, 13, and 12. Okay, so starting with the infinite norm, the infinite norm is 12. And obviously 12 is less than or equal to 13. That is, the infinite norm is less than or equal to the Euclidean norm. That's the conclusion here. By the values we've computed, these ones they are so obvious. We're not working with arbitrary numbers now, we're working with a specific example. The second one, starting with the Euclidean norm, which is equal to 13 by calculation. Now, the Euclidean norm equals 13 has to be less than or equal to the square root of the dimension 4, the square root of 4 times 12. What is 12? 12 is the Euclidean norm, and that is 24. So you can see with this evaluation down here, it shows that the Euclidean norm is less than or equal to the square root of n times the infinite norm. The n here stands for the dimension of the vector space. That's what the n stands for, the dimension of the vector space. So here is a four-dimensional vector space because the vector that we have here has four components. And that's why we're using 4 to multiply. And that's what gave us 24. Then the third equivalent statement is that the norm of the Euclidean norm, which is 13, is less than 19. And what's 19? L1. This one tells us that the Euclidean norm is less than or equal to LP1 or L1. Then finally, this tells us that the L1 norm is less or equal to the square root of n times the infinite norm, or times Euclidean norm. That is, the L1 norm is less or equal to the square root of n times L2 norm. So this is if the proof or the proof to the theorem, they are not so clear, not so visible to you. When we use numeric example to show, you see this is very clear and visible because we've already obtained these three norms as some numbers, and we can always compare real numbers together to see which is bigger because the set of real numbers has inequality defined on it. Am I communicating, guys? Can you all hear me? I hope you're following. Beautiful. Thank you, Bala. Okay. Is at any point, if you need more clarification, please don't hesitate to ask questions. It's very important that you grab everything we're talking about. Now we're moving to section 3.3. And now we want to go further into matrix norms. We have spent time talking about it describes the L1 norm, the L2 norm, and the LP norm. But the LP norm actually, the LP norm and the L infinity norm, where P can be 1, 2, 3, depending on how many. But of course, the specific LP norms that we have is when P is 1, when P is 2, and then when P is infinity. So let's look into the matrix norm. Definition. Please write. A matrix norm on Rm cross n, that is the set of all matrices over the field of real numbers, is a function, absolute value of dot, such that Rm cross n maps to elements of the real number system. So who can tell me how was the vector norm defined again? Bala, how was the vector norm defined? What's the symbolic representation of the vector norm? Bala, how was the vector norm defined? Is Bala no longer on this call? Mustafa, how was the vector norm defined? Bala, when you okay, talk to me, go ahead.
Come again.
How was the vector norm defined?
Sorry, sir, there's not the definition on the screen. We only have matrix norm.
Yes, I know we have matrix norm. That's because we are done talking about the vector norm. So before we go deeper into metric norm, I just want to review what you discussed under the vector norm. And that's why I'm asking you, how did we define the vector norm? Let me answer my question myself. So we said the vector norm is
Sorry, sir, 2 minutes.
a function that takes elements from Rn into R. This is the vector norm.
Okay.
That means yourself now.
Okay, this is the definition.
Yes, this is the vector norm. This is how it's been described as a function. Then now we are
Okay.
saying that the matrix norm is a function that takes elements
That
from
length of the
Rn
gate.
cross n into R. This is the matrix norm.
These three properties.
The vector norm, we also have matrix norm. We have dealt so much with the vector norm. Now we want to deal with the matrix norm. This matrix norm that takes elements from matrix spaces into the real number space must satisfy the three properties, which is just similar to what we spoke about under the vector norm. The first property, what do we call this first property? What's the name for it? I know this is the mathematical representation of it, but what's the name? What's the name for the first property? Christopher. Is Christopher on this call? What's the name for the first property?
Non-negativity.
Hello, sir.
No negativity.
They're not asking you now. Yeah.
Okay.
I'm asking Christopher.
Okay, Christopher answer.
Sir,
So what's the property called? This first property.
we have scalar multiplication. Okay, is it the first one?
Yes, the first one.
Okay, non-negativity. Hello, can you hear me?
I can hear you.
Yeah. The first one satisfies the property of non-negativity, sir.
Non-negativity. How about the second one? What's it called? Second property.
The second property satisfies scalar multiplication.
The third property.
The third property is triangular inequality.
Triangular inequality. Okay, the first two, you didn't get the first two correctly. The first one is positivity. The second one is homogeneity. Let's go back to it. The first one is positivity. The second one is homogeneity. The third one is triangle inequality. So please, I need us to remember these properties. Okay? So when you see them, you know what they mean. So this first property is positivity. Positivity. That's what this property describes.
But sorry, sir. Can you hear me?
Yes.
Well, I think there's no difference between positivity and non-negativity.
Yes. Go ahead. Yes.
Non-negativity.
Yes. I agree with you. So, positivity and non-negativity, they are synonyms. They are synonyms. They are the same thing, right? I just wanted to hear you call it what I called it earlier. But I'm saying that should you be asked this in an examination situation, if you say it is non-negativity, you are still absolutely correct. Nobody will penalize you for that, all right? Because I used a particular term in this class, I was hoping to hear you use the same term, but I'm not saying that you're absolutely correct, you're absolutely wrong, or the other one. Then the second property, you don't say scalar multiplication is beyond scalar multiplication. That's the reason why I said you are wrong. The first one, if you say non-negativity, you're still correct. Non-negativity is equivalent to positivity. Then the second one is beyond scalar multiplication, because you are not just multiplying a scalar by a vector, but you are also checking for the properties of the magnitude of these quantities. So we took the norm of the scalar multiple of alpha and a, that has to be equal to the magnitude of a, which is the absolute value of alpha, times the norm of a. Okay, so that's it. So the same properties must be satisfied. The same properties must be satisfied: positivity or non-negativity, homogeneity, and triangle inequality. But there's one additional property for matrix vector, especially for square matrices. We often require another property called submultiplicity. Submultiplicity is a compound word. Submultiplicity. If you know that you're not very good at pronouncing words like this, don't try to, so I not bite your tongue. So this property simply states that the magnitude of the product of two matrices A and B has to be less than or equal to the magnitude of A times the magnitude of B. But this property is only applicable to square matrices. This is only applicable to square matrices, not column or row matrices. No, square matrices. Are we following? I hope you guys are noting down these things. Are you guys noting these things down? Are you writing down? Because you need to be jumping.
Yes, we're
All right, that's fine. Three point 3.2 induced operator. Induced operator norms. The most important matrix norms are derived from vector norms. The most important matrix norms are derived from vector norms. Definition 3.5. We want to define what we mean by induced matrix norm. What does the concept induced matrix norm mean? For a vector norm, the norm of dot P, whenever you see me write the norm of dots, subject P, the dots can be equivalent, can be equal to X, can be Y, can be Z, can be A, depending on whatever. So just like, so the dots here serve as, the dots serve the function that variables serve in algebra. Remember, in algebra, if we don't know a thing, or if any quantity will vary, we use variables to represent them, like X, like Y, like Z, and so on and so forth. Here in norm spaces, we use dots to name a variable norm. That's what it means. So when I say a vector norm and I put dots, absolute or norm of dot P, it means a variable. That dot can be anything. But if we're looking at a norm on Rn, the induced matrix norm is given by this. So what do we mean by induced matrix norm? It means that this is a norm that has already been defined in the vector space. I am picking that norm and trying to induce it in a matrix space. So this induced vector norm is expressed as the norm of P, which is equal to the maximum of the norm of AX subscript P over the norm of X subscript P. And this is equal to the maximum where the norm of X subscript P equals 1 of the norm of AX subscript P. Does this make sense? I don't know if this mathematical expression makes sense to you. So this is what we mean by the induced matrix norm. How do we interpret this norm? It's been interpreted as the maximum factor by which A can stretch a vector in the P norm. The maximum factor by which A can stretch a vector in the P norm. That is a direct interpretation of the induced norm. So let's look at a theorem that backs up this idea of induced norm. Theorem 3.2. And this theorem actually helps us to look at some properties of induced norm. Please write. Induced norms satisfy 1. The norm of AX subscript P is less than the norm of A subscript P times the norm of X subscript P for all X. This is the first property of the induced norm. The norm of AX subscript P is less than or equal to the norm of A subscript P times the norm of X subscript P for all X. 2. The norm of the product of two matrices A, B is less than the norm of the product of A times the norm of the product of B. This is what we saw earlier, which is sub-multiplicativity. You can see how this word is messing up with me, right? That is the multiplicativity property. And the third property of an induced norm is that when you take the norm of the identity matrix subscript P, that norm must always be equal to 1. That is, the identity matrix has a norm of 1. And that is expected. That is expected because the identity matrix is just a matrix with values that run across the leading diagonal to be 1. Hello? This is yes, gentlemen and lady, Sorry for the break in transmission. I had to speak to a colleague of mine. So, am I back? Can you still hear me? Can you hear me? Give me a reaction, please. Give me a reaction. You don't mind my dark face, because I'm backing the lights. That's why my face is not so visible again. Okay. Now let's look at the third property. Okay, we've talked about these three properties. Like I said, whenever you see an induced norm, right, that is defined on the space of matrices, these three properties should follow directly. If they are not all satisfied, then that norm is not the induced norm. Let's move on to section 3.3.3, computing induced matrix norms. So how do we compute these induced matrix norms? Theorem 3.3. Let's look at this theorem that covers the way to compute the induced matrix norm on L1, L infinity, and L2. For a matrix A in the Rm cross n, that is, if I pick any matrix in the set of all matrices of dimension m cross n, 1, the maximum column sum, which is like the first norm, is equal to the norm of A subscript 1, that's equal to the maximum of the sum of all the magnitude of Aij, where I ranges from 1 to n. I hope this makes sense. I hope this makes sense. When you have a 3 by 3 matrix, for instance, A11, A12, A13, A21, A22, A23, A31, A32, and A33. When you have this, sorry guys, 1 minute.
Sorry, sir. You mute yourself.
Yes, yes, I know I'm muted. I just took the permission to step out quickly. Sorry. I thought you guys heard me when I said giving. Okay, I'm back. I'm back now. So I wanted to expand this particular norm that we've just looked at, so that you understand this symbol, this symbolic representation. You know, in mathematics, we love to use symbolic ways to represent things. So what do we mean? What do we mean by the norm the maximum of all the summation of AIJs. So look at it, we have A11, A12, A13. Now, don't forget that the matrix is what? We have the matrix A, which is in R, M cross N. So if I'm representing this as IJ, right? IJ, I'm going from J from 1 to N, and I have AIJ. J represents the column position of the numbers. I represents the row position of the numbers. So I am taking the sum I equals 1 to M. That is, when you sum this row, sum the row, that is A11 plus A12 plus A13. Take the absolute value of this sum. Okay, then you have the sum of A21 plus A22 plus A23. Take the absolute value of the sum. Then the magnitude of A31 plus A32 plus A33. Then we want to take the maximum of all 1 to N, the maximum. So when you add this, which sum gives you the maximum value? That maximum value is what we refer to as the norm of 1, the induced norm, that is the maximum column sum. And here's the maximum row. Okay, sorry, the one I just did now, this one I did now is the maximum row sum actually. This is the maximum row sum. Then the maximum column sum is going to be A11 plus A21 plus A31. Then A12 plus A22 plus A32. A13 plus A23 plus A33. So the maximum column sum is this guy here. The maximum column sum. And then the maximum row sum is this guy here. Do you understand? That is what is equivalent to L infinity. So L infinity is a maximum row sum, while L1 is the maximum column sum. Are we following? If you have any matrix at all, you do the row and the column. If you have any matrix, so you can get the maximum row sum or the maximum column sum. Then we have the spectral norm. The spectral norm, that is a true norm. So how do we express the spectral norm? As A subscript 2, that is equal to the square root of lambda maximum times A transpose times A transpose times A, which is equal to sigma maximum of A. What's yes, sigma maximum of A is the largest singular value of A. The largest singular value of A. That is, when you look through the matrix, you look at all the values in the matrix A. Once you get the largest singular value of A, we refer to that value as the what? The spectral norm. So these are the three norms that we can look at from the theorem perspective of computing induced norm. So all of these particular theorems will not be proved, it's just for statement's sake. So please take note of this induced norm, or how to compute the induced norm. So whenever you're told to compute any of these induced norm, you know what is expected of you. Are we together? Are we following, please? Please give me reactions if you're following. Please give me a reaction if you can hear me. Just give me a thumbs up, please. Good. All right. Let's look at some examples here. Before the example, can you note down, write this down? The one norm and infinite norm are easy to compute. They are just sum. They are very easy to compute. While the two norm requires some eigenvalue computation, which is more expensive. So one norm and two norm, they are easy, right? Just get the maximum row sum or the column row sum. But this particular spectrum norm, the lambda maximum here is like the maximum eigenvalue. So you need to calculate some eigenvalue to get two. The first example we'll deal with is this: compute the matrix norm for A equals 1, 2, minus 1, minus 3, 4, 2, 2, 1, 3. So this is the matrix we want to compute the norm. For A norm, for the one norm, which is the maximum sum, maximum column sum, we'll be adding the columns together. So the first column is this 1, minus 3, minus 3. When we add them together, we get 6. The second column is what? 2, 4, and 1. When you add these two numbers, the absolute value of these numbers together, you obtain 7. The third column is what? Minus 1, 2, and 3. You add them together, you get 6. So, and the maximum of 6, 7, and 6 is obviously what? 7. That is the maximum column sum. For the row column sum, we do the same thing now. This time around, we are adding up the rows. The first row here is 1, 2, and minus 1. You add them, you obtain 4. And don't forget, we are adding the absolute value of those numbers. The second row is minus 3, 4, and 2. When you add these absolute values of these numbers, you get 9. The third row is 2, 1, and 3. You add the absolute value of these numbers, you get 6. So which means that the maximum of the sums 4, 9, and 6 is equals 9. That is the maximum norm A infinity. Guys, did you understand? I hope if I ask you to compute these norms, you know what I am talking about. Yeah? I hope you know what I'm talking about when I ask you to compute any of these norms, right? Hello? All right. So for the second norm, it requires computing eigenvalues of A, T, and A. Now, I'll give you guys this as an assignment. I'll give you guys this as an assignment. In fact, an exercise. Now, on this call, let's try to compute these two now. First thing first, I need you all to compute A transpose times A. Let's get back to matrix A. This is matrix A. Matrix A has the components, the elements 1, 2, minus 1, minus 3, 4, 2, 2, 1, 3. This is A. First thing first, what is A transpose? Someone show me their mic and tell me what the elements would have in A transpose. Mustafa Muhammad, what should be the numbers in A transpose? Unmute your mic and tell me.
Yes, I'm here.
Tell me the elements in A transpose. Go ahead. Go ahead. Mustafa, can you hear me? I'm not hearing if you're speaking. Unmute your mic and talk to me, please.
Sir, I can't see your screen. No.
Hey, wahala. So does it mean I've been speaking to myself all the while?
No. The thing just went off like now, like this.
Okay, Moses. Thank you, Mustafa. Moses, tell me the elements in the transpose of A. Column wise. Let's write it column wise. Moses.
one.
Go ahead. One.
Yes, sir. Although arranging it row wise.
Column wise. No, let's use column wise.
Okay,
Column
column
wise.
Okay, 1 minus 3, 2.
1 minus 3, 2. You are giving me the
Okay, but let
transpose.
me go like this now. 1, 2 minus 1.
1, 2 minus
1, 2
1.
minus 1. And minus 3, 4, 2.
Minus 3, 4, 2.
And then 2, 1, 3.
2, 1, 3. Good. Please, let's give me a round of applause. That's correct. Next, I want everybody on this call, please take your pen and paper. Compute the product of A transpose A. Compute the product of A transpose A. We already have matrix A and its transpose. The next thing we want is to compute the product of A transpose A, because we're trying to compute the spectral norm. This spectral norm, we want to get the spectral norm. So what is the product of A transpose A? So I'll give you some time. I'll give you some time to complete that. I'll give everybody 3 minutes to calculate the matrix product of A transpose A. Everybody's hands should be on deck. Quickly, 3 minutes to do this. Once you've gotten an answer, raise your hand. I will give an opportunity to share your solution with us. 3 minutes. Your time starts now. Okay, Balala, go ahead. Tell me the products. Let me hear you.
I was hearing from your own.
I don't need to. Sorry.
Oh, wow.
Bala, please go ahead. Let me hear you. Alhaji Bala, your hand is up. You only say something. Who wants to answer the question? Please give me the products. What's the product of A and A transpose and A? Who is answering my question now? Bala, your hand is up. You want to say something? Go ahead and give me the products. There's no time. Oh, okay. I see that. I see that you are all not willing to respond to my question. Bala, unmute yourself. Your hand is up. Just unmute yourself and speak. Excuse me. Christopher. Christopher,
Sir?
I need you to
Hello,
give
can you
me
hear me, sir?
answers, please. I can hear you, Christopher.
Sir?
Tell me the.
Is it for
Tell
the
me the
transport?
no, tell me
Sir?
the not the transpose, the products, the multiplication of A transpose A. Give me the answer.
So what I'm having here is 14. That's the
14.
first addition. 14
Are you
minus
calling
8
the row
minus
or the
1.
columns? 14 minus 8
The
minus 1, like this, right? Okay, the next one.
is the column I'm calling, sir. Can you hear me?
Yeah, I can hear
Hello?
you. Are you calling the
The
column or the
column
row?
is the column
14
first.
minus 8 minus 1. Yeah, go ahead. The second
Yes.
one.
Minus 8, 21, and 9.
Minus 8, 21, and 9. The third one.
Minus 1, 9, and 14.
Minus 1, 9, and 14. Okay. Did we all get the same answer, guys? Did you all get the same answer? Okay. That's okay. Now, let me confirm this. So I'm going to use Python to quickly answer this question now. Let me see if I don't know if Jupyter Notebook can easily open here. I don't like using sorry, Google Colab. I don't like using what's it called? Google Colab. Okay. So hopefully it gets to open here very, very fast. Let's see how to compute it. I believe you can all see my screen, right? Let's open a new notebook. At least I'm not signed in here. I know if you ask me to sign in, that's the problem. Okay. So let me see. Let me just add a code here. Okay, beautiful. I will not open a new notebook in the drive. I'll just do it here. I'll do it right here. Can you guys see my screen? I hope you guys can see my dark screen, right? I don't want to sign in. Is it by force? Good. Please, you can see my dark screen. Give me a thumbs up. If you can see my dark screen, give me a thumbs up, please. Okay. So I want to quickly use Python to answer this question, just to make it very fast. The package I need, the only package I need to get this done is NumPy. So I'll start by importing NumPy as LP. So that package has been put. I don't want to sign in now. You must log in to use. Oh, sorry guys. It's like I don't want to sign into this. Let me open Google Colab with my other accounts. It seems that I just have to sign in before I can continue in Google Colab on that. And I don't want to use that. Sorry, let me just open Google Colab here. Google Colab. That Netflix. So I'll be sharing a different screen now. I'll share a different screen. Okay, let me rename this as what? Num spaces. Okay, so I'll start again by importing NumPy as NP. Now, once I import NumPy as NP, the next step I want to take is to define the matrix. So let's define the matrix here. Let's define the matrix. And the matrix is what? Let's call this matrix A, right? Matrix A equal to, so how do you present a matrix here using NumPy? So I'm going to use NumPy array. In fact, it has given me a suggestion. NumPy array of these numbers. I'll change the numbers in the matrix. Please, someone should unmute their mic and tell me the numbers, tell me the matrix in row wise. What's the first row? The first row has 1, 2, and -1. Yes, the next row. Please, someone should unmute their mic. Help me very fast. Help me very fast. Someone should unmute their mic. Please help me very fast. There's no time again. What is the second row? Okay, Jonathan, go ahead.
-2, 4, 2.
-2, 4 what?
I mean -3, 4, 2.
-3, 4, 2. And what's the third row?
2, 1, 3.
2, 1, and 3. Okay, so we have defined the matrix A. If I should call A now, and just say A, it will print the matrix in, you can see it now, because I have defined the matrix A using NumPy array. Whenever I call A, it will print it out in this manner. Okay, now what do I want to do next? The next step I want to take is to, I'm going to use what is known as this our eigenvalue. You know, I've written a formula. What's the formula again? Let me write the formula here as a text. We said the formula is, let me see the formula from the note. The formula is, it's called the spectra, that is the norm of A. I'll write it as as the norm of A subscript P. I mean, this subscript P or subscript 2 is equal to the square root of lambda of A, the square root of lambda A, lambda of lambda of the max, the square root of lambda of max, times A transpose times A transpose max. Okay, I think this is supposed to be curly braces. Lambda of max times A raised to power T A equal to and this is equal to sigma max times A. This is formula, right? That's formula, right? Give me thumbs up. That's formula, right? If that's the formula, give me thumbs up. So this is what we want to compute. Now I have already presented A as an array. So the next step to be taken is to compute what is known as the product. That's the product we have just computed, A and A transpose. But the first thing I have to do is to get the transpose of A. Okay. What's the transpose of A? So I'm going to say AT stands for A transpose equal to, there's also a numpy function that allow you to get it. It's not necessarily numpy. Let's just say A.T. Let's run this. So if I call AT, now you see what just happened. This is how to write transpose in numpy. When you present your matrix as an array, the transpose is just A.T. Can you see that I've gotten the transpose of A now, which is 1, 2, minus 1, minus 3, 4, 2, and 2, 1, 3. Can you guys see my screen? Give me thumbs up, please. If you can see my screen, give me thumbs up. Good. So we have matrix A, we have the transpose of A. The next step that I want to take now is to compute that product. But before we do that, I want to take the product of AT times A. So how do I take the product? ATA equal to, so ATA means A transpose times A. I would say AT at, there's one operation called at A. And if I say ATA, let's see, okay, this is the answer again. So this is how to take the product. Let me write it as a comment. Sorry, let me write it as a comment here. Take the product of the transpose of A transpose and A. Then this one is compute the transpose of A. Compute the transpose AT of A. All right, so this one is to take the product of the transpose AT and A, and that's what the product gives us here. So I'm taking it one step at a time. All right. Then descend this matrix this is the matrix that Christopher gave me. I hope it's correct. I think it's correct. Let me check what I wrote down here for Christopher's answer. Minus 14, minus 81. So what do you notice about this matrix? What do you guys notice about this matrix? Who wants to say something? What do you notice about this matrix? Display the product of the transpose of A and A. So please, what do you want to say? What do you notice about the matrix?
Yes, sir. Sir, if one of the things I'm observing is the diagonal is increasing.
What do we call this type of matrix? What do you call this type of matrix? Let me write it down. Notice that the product of A transpose, notice that the product of A transpose, and A produces a symmetric matrix. It produces a symmetric matrix. That is the transpose of A, or A is equal to its transpose. If you take a close look at this matrix that we obtained here, you discover that the matrix is such that it is equal to the transpose, that is this product. When you obtain the product, when you obtain the transpose of the matrix we obtained, the transpose will be equal to the matrix itself. If you transpose it, you will get 14 minus 8 minus 1 minus 8 21 9 minus 1 9 40. So that kind of matrix is called a symmetric matrix. Please, am I communicating? Am I communicating, guys? So this type of matrix is called a symmetric matrix. Now, with this symmetric matrix, what else do we want to do? We will have to use the eigenvalue. So we want to use the eigenvalues of AT. So that is the next thing, compute. The next step I'll take now is compute the eigen, or how do you spell eigen again? Compute is EIGN, eigenvalues of ATA. So let's compute the eigenvalues of ATA. Someone's hand up. Jonathan, go ahead. Christopher, please let today you put me through today's class. So I'm not seeing the screen at all. Sorry about that, Mustafa. So let's compute the eigenvalue using Python. So the eigenvalue, there is a function, there's a package in Python that is called linear algebra, and inside that linear algebra package, there's a function called eigenvalues. So this is what I'm going to say. I will say eigenvalues. Let me use a variable called eigenvalues. Eigenvalues equal to, I will call my numpy len arg dot eigenvalues. So that is the function I'm going to use of ATA. You know, ATA is the product of the transpose of A and A. So if I compute these eigenvalues, let's display the eigenvalues. Let's see how they look like. So these are the eigenvalues: 30, 13, and 5. Those are the eigenvalues of the product of A transpose and A: 30, 13, and 5. I'm just calling a whole number without a decimal. Now, with these eigenvalues, what do we want to do? Remember the formula. What's the formula? The formula says we would have to compute the square root of the eigenvalues, the maximum of the eigenvalues, times A transpose times A. That is enough. So after computing the eigenvalues, you need to take the square root of the product. So what we'll do now is we're going to say, give me the square root of the maximum of the eigenvalues. Are you following me? Give me the square root of the maximum. We want to take the square root of the maximum of the eigenvalue. So let's call this the spectral norm. Spectral norm is equal to the numpy. We're going to use this numpy square root of the maximum of these eigenvalues that we computed. The maximum of the eigenvalues that we have computed. Now with this, we can now say that print, I'd like it to print I'll use the F string, print the, call it the spectral norm, print the spectral norm of what? Print the spectral norm as is what? The spectral norm is, we have the spectral, yes, enter. Guys, so this is the spectral norm. The spectral norm of the matrix is equal to 5.514. Can you see that this spectral norm is the norm that is a little bit, it might take time, and this is even shorter here because we're writing codes for it. So imagine that you have to calculate the eigenvalues manually. First thing first, of course, taking the product is not a problem, but getting the eigenvalue would, take a little bit time using manual process. Once you get the eigenvalue, you now take the square root of the maximum eigenvalue, which is the square root of 30 points this. When you take the square root of that, that gives you the spectral norm of that matrix. Am I communicating? Does it make sense, guys? Are we following? No reactions. You guys should learn how to give reactions in class now. Okay. So let's get back to our lecture notes. Okay, so I said we're going to complete this later, and we've completed it, right? That's this one. So that means we have done all of them, completed all the norms. This has been done. Okay, we still have some minutes to. Now let's talk about the Frobenius norm. The Frobenius norm. What is the Frobenius norm? Definition 3.6. The Frobenius norm is defined as norm of A subscript F, where F stands for Frobenius, is equal to the square root of the double sum of AI squared, where I start from 1 to n, j stands for 1 to n, and this is nothing but the trace, the square root of the trace of the matrix ATA. The square root of the trace of the matrix, the product of the transpose and the transpose of A and A itself. So my question is, what is the trace of the matrix? I hope you get everything. What is the trace of the matrix? That's the question. What is the trace of the matrix? Olamide, I'd like to hear from you now. Olamide, what is the trace of a matrix? What is the trace of a matrix?
What is this? What are you looking for? Who is that person? It's okay.
Okay. It's like my network is not so strong from your side. I mean, your network is not so strong. Let me answer my question myself. Already, I have it on my notes. I said where TR denotes the trace. And what is the trace? The trace is the sum of diagonal elements. The trace of a matrix is the sum of diagonal elements. So if we have matrix A as, if our matrix A as 1, 2, 3 minus 1, 2 minus 1 minus 3, 4, 2, 2, 1, 3, it means that the trace of A will be 1 plus 4 plus 3. That is the trace of A. It will be 1 plus 4 plus 3. Very simple. And that's equal to what? 8. That is the trace of A. But the Frobenius or the Frobenius norm is saying that that norm is nothing but the trace of the square root of the trace of the product of A transpose and A. And we have already obtained the matrix A transpose A, which Christopher gave us earlier. The matrix has the following elements: 14 minus 8 minus 1. Let's write it down. 14 minus 8 minus 1. Then minus 8, 21, 9. Minus 8, 21, 9. Then finally we have minus 1, 9, 14. Minus 1, 9, 14. This is the matrix that serves as the product of the transpose of A and A itself. Is that correct? That's the matrix. So the question now is this: what is the trace of A, T, A? The trace is going to be 14 plus 21 plus 14. So what is 14 plus 21 plus 14, guys? What is 14 plus 21 plus 14? Drop your answer in the chat box. Please drop your answer in the chat box.
Sir, please come again.
I mean, sum those numbers up for me. 14 plus 21 plus 14. That is 49. Good. So this is equal to what? 49. This simply means that the Frobenius norm of A is equal to the square root of 49, which is equal to 7.
Yes. You want to do something? I want to.
Are we together?
Oh, okay.
Are we together, guys?
Yes.
Fantastic. So let's drop some remark here. The Frobenius norm is one easy to compute. It is just sorry. Okay, no, it's correct. It's correct. It is just the sum of squares. The Frobenius norm is easy to compute. It is just the sum of squares. 2, not an induced norm. It doesn't come from a vector norm, so it's not induced. 3, it satisfies. No. 3, it satisfies submultiplicativity. It satisfies submultiplicativity property. That is, the product of A of Frobenius less than or equal to the product of AF times the product of BF, the norm of A and norm. The 3, related to 2 norms, is related to 2 norms, that is, the norm of A 2 less than or equal to the norm of AF less than or equal to the square root of N times the norm of A. So these are the properties or some remarks that follow directly from the Frobenius norm. Are we making sense? Please, I hope I'm making sense here. Good. Good. Let's move on to example 3.5. We've already completed this example. We've done it. So you see that the trace that we've calculated using the trace, the answer we got is 7, And even this example, if we decide to take the square of all the elements of matrix A, we still obtain 7. Can you see that? So two different methods, we arrive at the same answer, and that is also gotten from the formula. We said it is the summation of all the m I to m j I to m square of it, which is equal to the trace of the A transpose. That's all about the Frobenius norm. Do you have any question about the Frobenius norm before we move on? This class will end by 12:30. Any question about the Frobenius norm, please? No question. Beautiful. Now, let's look at the condition number of a matrix. Remember that this is what we started with. So we have to first of all introduce the vector norm, the matrix norm, their properties, and now we are back to the main goal, which is the condition number of the matrix. Let's start by definition and interpretation. Definition and interpretation, section 3.4.1. Definition 3.7, condition number. What's the condition number? For a non-singular matrix A, which is in the set of all square matrices. Who can remind us of the idea of non-singular matrix? When is a matrix set to be non-singular? I know I explained it the time we had our physical lecture the other day. Drop the answer in the chat. When is a matrix set to be non-singular? When is a matrix set to be non-singular? I want to see your answers in the chat box, please, quickly. When is a matrix set to be non-singular? When is a matrix set to be non-singular? Okay, that's very correct. I can see Jonathan said when determinant of matrix is not equal to 0. And Joseph also said when its determinant is not equal to 0. That's correct. So for non-singular matrix A in is an n by n set and a matrix norm, the condition number of A, which is represented as the kappa of A, is equal to the norm of A times the inverse of the norm of A. For a specific norm, the kappa of this P of A is equal to the kappa P of A times, when we say specific norm, it means it can be kappa of 2 of A, that's equal to the L2 norm of A times the L2 inverse norm of A. It can be L1, it can be L infinity. That is what we mean by specific norm. All right, that's how it's defined. So there are some properties of the condition number that is important that you know. Please write them down. I hope you guys are writing all these things down. Before we go to the I'm giving these properties as a theorem. Properties of condition number as a theorem, theorem 3.4. properties of condition numbers. Number one, this one is supposed to be down here. This is number one. The kappa, this is not kappa, it's kappa. The kappa of A is always greater than or equal to 1 for any non-singular matrix A. The kappa of A is always greater than or equal to 1. That's the first property. The kappa of A is always greater than or equal to 1. That means you cannot solve kappa of a matrix and you obtain something like 0.5 or something like 0 or something like 0.8. If you obtain that, it means that your computation is wrong. Property 2. The kappa of the identity matrix is always equal to 1. This is best possible. It's always equal to 1. The kappa of the identity matrix is always equal to 1. Number 3, the kappa of a scalar multiple of alpha times a matrix A is equal to kappa of A for all scalar that are not equal to 0. This means that if I ask you to calculate the kappa of 15A, for instance, the answer is nothing but the kappa of A. Whatever number that stands here, whatever number you have here, is always going to be equal to the kappa of A. So if you see your exam, you're told to compute the kappa of, say, 3757A. Just know that you don't have to stress yourself computing this number because the answer will always be equal to the kappa of A. Is a theorem that has been proved. Am I making sense? Then the fourth property says that the kappa of A is always equal to the kappa of A inverse. The kappa of A is equal to the kappa of A inverse. And the fifth property says for orthogonal Q, such that the kappa 2 of Q is equal to 1. For orthogonal Q, the kappa 2 of Q is equal to 1. Looking at talking about the kappa in the Euclidean space. The kappa of Q in the Euclidean space. So when we say for orthogonal Q, it means that Q is an orthogonal matrix. Whenever you have the orthogonal matrix, when you compute the Euclidean kappa of Q, the answer will always be equal to 1. And there are proofs that follow. I think I gave just one proof. The proof for the kappa of A, which is the first condition or the first property. Kappa of A being equal to 1. I started by saying 1. Of course, we know that the kappa of we know that the norm of I is always 1. So 1 is equal to the norm of I, and norm of I is equal to A times A inverse, and this is less than or equal to the norm of A times norm of A inverse, and that's equal to the kappa of A. This is very straightforward to see. It's very straightforward to see. That is just the end. So it's very direct and straightforward proof. So it's not something that is so hidden and difficult to understand or to unravel. If you have any questions, please ask. If you have any questions, ask, please. Oh, I just got your question. I just got your message now. Moses, why didn't you raise your hand and speak? You should learn how to talk. We guys are 400 level students, so you should learn how to be very, very audacious, bold, and not to be timid. I will shut you up if you raise your hand to speak. I'd have allowed you. I just saw a message on WhatsApp now, Moses. All right. So I think we'll be ending this class at this note. I'll just inform that the Christians here have some fellowship to attend by 12. I will stop here, and by Monday, we will complete this topic. By Monday, we'll complete this topic, and we shall also, yes, we'll complete this topic by Monday by the special grace of God. So thank you guys for joining today's class. I also have some Python implementation. I'll try my best before Monday to make sure that the materials All the whole course lecture is available on our website, and the recording of today's class and yesterday's class or the previous class will also be available on the website. I wish you guys all the best. Thank you for joining today's class. I hope you enjoyed today's class. Network was not so terrible. Let's go for that. All right, see you again in the next one. Have a wonderful day ahead.